All right, we're going to talk about histograms in section 2.2 here. That's all we're going to talk about today. And we'll use histograms to talk about frequency polygons in the next couple days. Histogram, by definition, a bar graph consisting of contiguous or adjoining or adjacent touching boxes. The graph consists of a horizontal and vertical axis. The horizontal axis is labeled with what the data represents. Vertical axis is the frequency or the relative frequency. If it's frequency, obviously it's just how many times we see it. If it's relative frequency, your y-axis is going to be in decimals or percentages from 0 to 1. Nice thing about the histogram, it gives you the shape of the data, tells you the kind of the distribution of the data, can show you the center, can show you the mode, shows you how spread out, and can show you if it's bimodal, unimodal, that kind of thing. Some pitfalls of it are if my data values aren't spread out very far, it can be kind of a very basic image. If I don't have a lot of data, let's say I've only got like 6 pieces of data, that's going to be a terrible thing to use to display my data. Going through this, you're going to see some abbreviations: F for frequency, N for number of total data values, and an RF is relative frequency, which is found by taking frequency divided by the number of data points. There are certain structures that we use for creating a histogram. Now, some of these, like some of the other stuff we've seen so far in statistics, there's flexibility. Some authors use all of these principles, all these procedures. Some leave some out. I'm going to try to give you the kind of the most stringent, most involved process, and then if things get left out in examples that we see, then so be it. But the number one thing we're going to do is make a frequency table, our distribution table that we've been working with. We're going to do relative frequencies and cumulative frequencies. We'll do class limits and class boundaries, and we'll do midpoints. Those are all things that are going to be used in histograms and or upcoming graphical displays that we need to mess around with. We're going to place boundaries on the horizontal axis and obviously frequencies then on the vertical axis. So for each class of the frequency table, draw a bar whose width extends between corresponding class boundaries. So for histograms, the height of each bar is the corresponding class frequency. So for relative frequency histograms, the height of each bar is the corresponding class relative frequency. All right, so this data is great, and we'll do this example, but I actually want to come down and do, I got to cut and paste it. Give me a second. Got a alternative example here that I think is maybe a little bit better to deal with since the values are whole numbers here. 50 highest temperatures of 50 states. Looking through this, what we're going to do first of all, we're going to set up our class limits like we have done so far in all the other frequency distributions. So the highest value here is 134. The lowest value is 100. I want 7 classes. We said that the rule, like the square root of the number of data points, that'll be fine. If you want to go with less classes, that's fine. I just wanted to go 7 here. The width then is going to be our range, which is 34, divided then by 7, which that's like 4.8 something. So I'm going to round that up to 5. Always round up your class widths. Now the one part that we've got to pay attention to, and this is the reason I wanted to show this one first, is our class boundaries. This is new to us. Our class boundaries are created by taking our most precise data, meaning that, since they're all whole numbers, that's our precision, is to the nearest unit, nearest degree here. So then what we will do with our class boundaries is we'll go one more decimal place. So if this is the whole number, then our class boundaries are going to be to the tenth. If I had a number here like 105.3, so that's the greatest precision is to the tenth place. So then my class boundaries I would write to the hundredth place, and that's the reason I want to do this example first. All right, so class limits. We're going to start with our smallest piece of data, which was 100. And then I'm going to add my class widths. So it'd be 105, 110, 115, 120, 125, and 130. And then if you remember, we went 104. So it was one less than this one. And then we can go 109, 114, 119, 124, 129, and then 134. So those are my class limits. Okay. Now class boundaries, those are found. What I'm going to do, I'm going to take this number here, and I'm going to remove one level of precision from that. So, like I said, since these are all whole numbers, I'm going to remove, in this case, 0.5. So this class boundary is going to be 99.5. Now, class boundaries and class limits still have to have the same width. So I'm going to add 5 to that, and I get 104.5, 109.5, 114.5, 119, 124, and 129.5. Then the upper class boundaries, so these are contiguous, so meaning that this first upper class boundary is actually this lower class boundary. So I'm going to go 104.5. And then this one is going to be that one. Or I can just keep adding that class width to these. So 114.5, 119.5, 124.5, 29.5. And then, so the next one would be, so at 129, so this one here would be, what, 134.5? And what that does, if you think about this, what's going on, if I were to graph my histogram with just these class limits, and those were on my x-axis, there would be a gap of 1 unit between them. Okay, and potentially there could be, depending on the precision, there could be, like if I had a 104.5 as a value up here, and I graphed my histogram with just my class limits, the 104.5 number or piece of data would not exist on my histogram. It'd be a piece of data that got left out. Class boundaries eliminate values getting left out, and it also creates a situation where my my boxes in my histogram are going to be contiguous. All right, so I'm going to take and now find the midpoints. They didn't put a column here, but it's not too hard to add one in. So midpoints. So midpoints are going to be of the class limits or the class boundaries. They end up being the same point. You add these two numbers together and divide by 2. So it's going to give me 102. Add these two together and get 107. What you're going to find out is that the class midpoints are also going to be the same as my class widths, or they're going to vary by the same as my class widths. So the next one's going to be 112, 117, 122, 127, and then 132. Those are my midpoints. My frequency, so I'm going to take a minute. I'm going to pause this. I'll count these up. I think that's something you guys can do without instruction. Okay, so I went through, created the frequencies, or counted the frequencies. The next thing that we might want to add to these would be our relative frequency. So there were 50 states, so obviously 2 out of 50, 8 out of 50, 18, 13, 7. All right, so then we could go ahead and say, okay, well, that's 0.04. This is 0.16, 0.36, 0.26, 0.14, 0.02, 0.02. We could go ahead and use that information then if they asked us to create a relative frequency histogram. We can talk about the difference between a frequency histogram. Frequency histogram, all it's going to be is the, oh, that's not the one I want. All right, so with a frequency histogram, what we're going to do, and this would be the same for a relative frequency histogram, the x-axis is going to be your data. Okay, so down here, it was our temperature of our states. And it's going to be marked using your class boundaries. So our interval is going to be 99.5. And I'm going to, just so this looks nice and clean, I'm just going to create what I want my width of my boxes to look like. So I'm just going to kind of try to duplicate that. All right, so your x-axis is going to be marked with your class boundaries. So go ahead and done that. This says 104.5. That's the one that says 109.5. And 4 and 9 look the same. Set up my y-axis. So this is the frequency. Okay. And you can structure this the way you want, what makes sense to you. I thought going by threes made sense. And now you're just going to go through and say, okay, between 99.5 and 104.5, what was my frequency? It was 2. So I'm going to graph a height of a box with a height of 2 here. Kind of got to guess a little bit based on my y-axis. But then we'll go to the next one, and it's a frequency of 8. So jump up to 8. And we're good to go. 18 is the next. Then we've got 13. 7. A little bit above 6. And then the next two are both 1. So we'll kind of do something like that. And that's my histogram. So it gives you an idea of where your data is centered, okay? Centered here, kind of in this interval here. A lot of times with histograms, they're going to tell you your center, visually give it to you. They'll tell you the mode, okay, which one occurs the most, which class is occurring the most. Now, if I was to ask you to create a frequency, a relative frequency, all that would change is that you would rewrite these in terms of these, okay? And what you're going to find out is if I put a relative frequency right next to just a frequency, the distribution, the shape should still be the same. Nothing there would differ. One thing that I want to talk about is this example. In this example, it's 100 soccer players. I've taken the heights of them. We'll talk about the class limit. So what I wanted to do here, I'm just going to say that I wanted, let's say 8 classes here. So I'm going to take my small, so I've already got these in order. So my range would be 74, that's my largest value, minus 60, my smallest value. Gives me a range of 14. I'm going to divide that by 8. I want 8 classes. That's going to give me, I think it's like it might be like 1.75. I'm around, so 1.7-ish. But whenever we get our class widths, it's a good idea to round those up. I'm just going to round up, just to make things convenient, we'll round up to 2. And that's something that's flexible. That is, I round up to the whole number. I think you'll see a lot of instruction in other places to round up to the whole number, but you can round up to a 10th place. You can round up to the 100th place. It's just going to make your class limits a little bit nastier if you do those. So I'm going to start at 60, and then 62, 64, 66, 68, 70, 72, 74. And then remember how to get the upper limit of my classes. It's 1 less than that one is going to start. and then I can keep adding my class width should be +2 here, should be +2 there. I think that's the way I like to do it. Um, 73, and this one's going to be 75. So if I left my class limits this way, think about what's going to happen if I graph. Like, let's say I've got a class limit of 60 to 61, and I use that on my x-axis, and then I've got one of 62 to 63. So let's say that I find a frequency of like 3 here for 61 to 60, or 60, 61, and let's say I have a frequency of 5 of 72, 73. And those, I don't know, I'd have to go look at the data. I'm not sure about these. They're probably wrong. But you see that creates a gap here. There's no longer we're not abiding by the definition of a histogram. They have to be contiguous. And the issue, even further exacerbated by the fact that there was a 61.5 up in my data. If I were to scroll up there, 61.5 is right there. It's not being calculated in that, and it's not being calculated in that. So it's not showing up in my graph. Therefore, my graph would be a misrepresentation of my data. So to alleviate that, what we do is we take our class boundaries, we find our greatest precision. So our greatest precision throughout here is 0.5. So then we're going to, in our class boundaries, we are going to go one more decimal place than 0.5. So we're going to the hundredths place. So what I'm going to do is I'm going to subtract from that number right there 0.05. So it gives me 59.95. Now to find my class boundaries, I'm just going to now add my class width that I wanted to each one of these. Okay, so 59.95, I want to add my class width, and it should be 61.95. Class width was 2. 63.95, 65.95, 67.95, 69.95, 71, and then 73. And what you see then is that puts us in each one of these classes a little bit to the left of those lower limits. Now, they have to be contiguous, so this upper limit here is going to be that value there. And that makes sure then that I'm contiguous. And then I'm just going to keep adding 2 to that, so it'd be 63, 65, 67, 69.95, 71.95, 73.95, and then if I was going to add 2 here, it'd be 75.95. So that's going to be what this one is. Now I've got my class boundaries, and what's nice now is when I go through and I find my frequency, if I would have left it as class limits, I wouldn't have known where to put this 60.5. But now, because I have my class boundaries, I know that 60.5 should go in this first class. My midpoints, add these two numbers, divide by 2, so it gives me 60.5, 62.5, 64.5. Again, you're seeing the class width being demonstrated in between each of these. All right, now I'm going to go through and count these frequencies for us. All right, so counting those frequencies that, again, fell in these class boundaries. I got these. So relative frequencies then, these were all out of 100. So this 5 out of 100 would be 0.05, 0.03, 0.15, 0.4, 0.17, 0.12, 0.07, and 0.1. If we summed our frequencies, terrible sigma. If we summed our frequencies, obviously it would give me 100. If I summed the relative frequencies, that's going to give me 1. Cumulative frequency, again, 0.05. Now I'm going to add this one to that, so 0.08. Then I'm going to add this one to that, so 0.23. then 0.63, 0.8, 0.92, 0.99, and then 1.0. Again, the cumulative frequency is not a big deal on histograms. We don't use that, but when we start talking about ogives, which is in the next couple of days, we will use that. So now I want to construct a frequency polygon, or sorry, frequency histogram for this data. A frequency polygon is what we'll talk about tomorrow, and it is directly related to this. So we're going to construct our, let's do a relative frequency. Let's use this column here. So our x-axis is going to be heights. This here is, like I said, is going to be relative frequency. So I'll just say RF. My highest relative frequency is 0.4, so that's what I'm going to do up here, 0.4. Then halfway would be 0.2. Got 0.1, 0.3, 0.05, 0.15, 0.25, 0.35. So now we got to put our class boundaries. This is where it kind of gets messy sometimes. So 59.95, and then we're going to go 61.95, 63.95, all right, so I just went through and wrote all my class boundaries down, and now it's just a matter of, this first class was 0.05, so 0.05. This right here is my midpoint. If you want to put that in there, you can. It's just going to get cluttered right now if I do that. 0.8, maybe about right there. And now what's nice is that there were no data points that, if you remember that 60, I think it was 60.5 in this image here, or I guess 61.5, that data point is now inside this, it's showing up inside this bin here, and it's not missing. So I got an accurate representation of my data now. Next one's 0.15. Next one's 0.4, so that's all the way up here. Obviously, we want to make these as rectangular as possible. 0.17, approximately there. 0.12, 0.07, and the last one is 0.1, so about right there. And again, it gives us a good visual of our distribution. Like I said, though, if we would do frequency, you know, think about this. Is that 40 comparing to 15, the same as 0.4 is going to compare to 0.15? So the structure is going to be the same. It's just the way that we label our axes that would look a little bit different. If we ever want to do discrete data, so this one is a situation. This is one probably that you're most familiar with, and I'm not even going to make a distribution table of this. But discrete data, remember, is things that are countable. So this is going through and talking about how many books were bought by 50 part-time students. So we had, you know, number of books. So 11 people bought one book. 10 people bought 2 books. So usually what happens here with this kind of stuff is we do, if I take the idea that my most precise value is tens or sorry, the units place, then my data then needs to be 0.5 in regards to, or my x-axis needs to have that precision of 0.5. So what I'm going to do here is I'm going to start at 1 and go to the left 0.5. and then to the right, I'm going to go another 0.5, so it'd be 1.5. And then I'm going to be 2.5, 3.5, 4.5, 5.5, 6.5. Okay. Now, what I think is interesting here and nice to see that that's one. There's two halfway in between there. So these midpoints are all these values here, the discrete value data values, which a lot of times when we have discrete value, I don't say a lot of times, most times when we have discrete values, or all the times we have discrete values, the midpoint ends up being usually what we use for identifying our bars and our histogram. So I'm going to maximum 16, so let's go 8, 4, and 12. So 11 people bought one book, so I'm going to create this here, and what you're going to see most of the time, there we go, is this first box. You might not see people write that and that. They'll just identify this first box by the midpoint coordinate, because that's what's descriptive of this box. It means how many people bought one book. 11 people. Okay. How many bought two books? 16. And then you probably wouldn't see that 2.5 there. Okay, there's nothing wrong with writing it. More information obviously is better in most cases, but oh, I did that wrong. I missed this. My fault. Look, 2 was 10. So just under that one. And then 3 was 16. Apologize for that. 4 was 6. 5 was 5. And 6 was 2. So you see it that way, but like I said, a lot of times with discrete data, you often just see the midpoints being the descriptor for the x-axis. Tomorrow, we will take the information that was explained here, and we will start talking about what a frequency polygon looks like. You see the first step in creating a frequency polygon, says you have to create a histogram. After that, it's pretty easy, actually.